Hello, this is the next video in a playlist that I'm calling Introduction to Mathematical Statistics, and we're in chapter 4, part of this playlist that I'm calling Joint Distributions. And today's topic is the bivariate moment generating function. So in this section, we'll assume we have a random variable, x and y, so it's a vector with known density f. X, our random variable can be discrete or continuous. And this is how you define a bivariate moment generating function. So m of xy, and the xy tells us a bivariate moment generating function of t1 and t2 is the expected value of e to the t1x plus t2y. Now if we expand e to the x using a Maclaurin series, we get this expression here. Then we're going to expand the numerator using the binomial theorem. So the sum from n equals 0 to infinity and the n factorial remain the same. And then we write this expression using the binomial theorem. And then e is a linear operator, so it goes into each term. And the only things random here are x and y. So if we distribute the j and distribute the n minus j, it ends up being this. The expected value goes in, and really it's e to the xj, y to the n minus j. And then everything else is a constant. And that's it. So that's the bivariate moment generating function. Now, in a lot of cases, you just leave it as the definition, and then you either sum it overall, x and y times the density of x and y, or the integrated overall x and y times the density of y. And you derive it like this. But what we're going to show is that, how to find moments using the moment generating function. And this last expression is easier to do that with. So what I want to do is write out a few of these terms. And I copied it down so it doesn't go off the screen. So when n equals 0, we get 1 for this sum. When n equals 1, then we get these two terms. When n equals 2, then this is, written like this. It goes from 0 to 2, and we'll expand that in a second. But then when n equals 3, then we get this sum of 4 terms. Now let's expand each of these sums. So of course, the first 3 terms just come down, and we expand these, and we get 3 terms, these here. Notice the 2 factorial on each of these, but this term is 2 times this expression, which cancels with the 2 factorial. And then this expression, there's 4 terms, which are these 4 here. And the 3 factorial is for the first and last terms, but when you expand this, you get a 3 as a coefficient, which cancels with one of the 3's in the 3 factorial. And so this is it. And so we're going to take this expression, start taking derivatives of it with respect to t1 and t2. So let's differentiate it with respect to t1 first. But let's go up here and see what we would achieve. So this is 0, and then we're left with e to the x when we take the derivative with respect to t1. This is 0. This term is 0. Here we'd get t2, e to the xy, expected value of xy. Here the 2 would come out front, cancel with one of those, and we're left with t1, expected value of x squared. This term drops out. Here we would be left with t2 squared, expected value of x times y squared over 2 factorial, and etc. So it is this term here, and that's what we would get. Now to find the moments, we have to evaluate this at t1 and t2 equal to 0. So if we plug in t1 and t2 0, notice that every term drops out but this first one. And so the first derivative of the bivariate moment generating function with respect to t2 evaluated at t1 equals 0 and t2 equals 0, we get the first moment of x. Now, let's differentiate this with respect to t2. So if we look at this expression and then take derivatives with respect to t2, this is a constant, so it's 0. Here we just get the expected value of xy. This is 0. Here the 2 cancels, leaving 2t expected value. Here we get t1, that's constant, and then so forth. Then if we evaluate it at t equals 0, t1 equals 0, and t2 equals 0, then notice that every term cancels except for this, the product moment here. And that's it. So we're generating moments, taking derivatives of this and then evaluating at t equals 0. In the general theorem, we have a random variable xy, so we're in the bivariate setting with known density f. And a random variable can be discrete or continuous. Then the product moment of order k, where k is k1 plus k2, is given by this expression. So we take the kth derivative of our moment generating function, with respect to t1, k1 times, and with respect to t2, k2 times. We evaluate it at 0, and that is the expected, it's the product moment of order k. So x to the k1 and y to the k2. And that's how we do it. So let's look at a quick example using the bivariate normal moment generating function. Now we're not going to derive it, but we'll list it, and then we'll take a derivative and find the moment. So assume we have a random variable xy, and I put a transpose because really I want to think of this as a vector, column vector, with known bivariate normal density f, and that's a well-known density. The mean of our random vector is mu, the vector mu, which can be thought of as mu x, the mean of x and the mean of y. And the variance of our vector creates a variance covariance matrix. The variances are down the diagonal, and the off diagonal is the covariance between x and y. And I just noticed that, well, I'll show you in a second. So then the density can be thought of as this. So the moment generating function of the bivariate density xy, is e to the t with this exponent. Now, going from this line to this line, instead of calling it mu x, mu y, I call it mu1 and mu2. And I'll correct that in the hard copy. But then this expression, of course, is correct. If you multiply that out, you get these three terms. Now, to find the mean of x, the expected value of x, we use the moment generating function, the bivariate moment generating function, take the derivative of it with respect to t1, and then evaluate it at t1, t2 equals 0. So the first derivative of this, notice it's an exponential function, so we get it back. And the chain rule says take the derivative of the exponent with respect to t1. So here we get mu1, that's 0. The 2 comes out front, we get t1 x1. Here we get just t2, the covariance between x and y. That's constant. So this is it. Now let's evaluate it at 0. And the theorem says that's going to be the mean of x. And notice that when you plug in zeros here, we get 0 in the exponent. E to the 0 is 1. These are 0. And the only thing left is mu1, which is the mean of x. So the theorem, at least in this example, is correct. Now let's use R to find some crazy moments, product moments of a bivariate normal. And I'm going to have to point you off to a video I created called Symbolic Derivatives Using Base R Software. And there we listed this function. And it's actually, if you just Google symbolic derivatives in R, this expression is almost in every video. But we create an expression which is the bivariate moment generating function. And then we start taking derivatives. So we take the first derivative of it with respect to t1, and we'll store it here. We take the second derivative with respect to t1. Then we take the derivative with respect to t1 and then t2. And here we take the third derivative with respect to t1, and then the second derivative with with respect to t2. Now let's create values for our parameters: 5, 10, 4, 17, and covariance 17. Let's let t1, t2 be 0, and let's evaluate that first moment. And we should get the expected value of x, or and notice it's 5, and it should be 5 because we let the mean be 5. Now the second derivative with respect to t2, so we take it twice, that would be the expected value of x squared. When we evaluate it, we get 29. And if we remember the formula for the expected value of x squared, that's the variance plus the mean squared. And notice we get 29, as we should. Now if we evaluate the moment generating function, where we've taken the derivative with respect to t1 and then t2, we get 67. So that's the expected value of x times y. And if we remember our formulas, that's the covariance plus the product of the means. And notice it's 67, as it should be. And then let's just evaluate a crazy expression. So the expected value of x cubed times y squared is going to be 59,895. Now I was going to print out this expression and then maybe try to simplify it, but one downside about R is it doesn't simplify that derivative, but it's correct. So it would have taken up a couple pages or more to print it out. But this is it. Well, that's all I have for this video. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.